Welcome to Study Loop.
This is the answer to Chapter 17, problem number 55 from the Smith Organic Chemistry textbook. And in this problem, we're given three molecular formulas and spectral data for each formula, and we're asked to use that to come up with a structure for each one. Okay, and so I already have some stuff written here. The stuff written in black is all the information we were given, and then the stuff written in green is how I started each one. So I tried to record an answer to this just now, and the video was too long to upload, so I'm going to leave them drawn out to try to save some time. So for each of these, I'm going to start by calculating an HDI. So for A here, it's 4. And I calculated it by 2 times the number of carbons plus 2 minus the number of hydrogens over 2. And so it comes out to 4. So the IR data that we're given doesn't tell us much. We have carbons, sp2 and sp3 carbons bound to hydrogens. And then we have these peaks at 15 and 1600, which are characteristic of a benzene ring. And so that agrees with our HDI. Anytime that you see an HDI of 4 or more, you should know that a benzene ring is a possibility because the ring counts for 1 and then the 3 double bonds count for 3. So 4 or more, think potentially a benzene ring. Okay, so looking at the NMR data, this first signal is probably going to be 2 methyl groups. This next signal is going to be 1 methyl group. That's going to be unlike the first 2, obviously. The third signal integrates to 1. And so if we look at the first signal and the third signal, they're splitting each other. And so this tells me that we have an isopropyl group, and the third signal comes from that single hydrogen on the isopropyl group. And then our last signal, the multiplet between 7 and 7.4, is going to be our protons on the 6-membered aromatic ring. And since the integration here is only 4, that tells me that this ring is di-substituted. And I'm actually going to move this over a little bit. Whoa. So that's from when I answered this earlier. Okay, so there we go. So what are you? All right. So we have, oh man, there we go. All right. So we have a di-substituted ring, as I said. And so one of our substituents is going to be our isopropyl group. And the other one is going to be that methyl group, that's signal 2. However, we can't distinguish between ortho and meta here. So we can say that it's not para, because if it were para, we would expect 2 distinct signals. So instead of a multiplet for the aromatic protons, we would expect 2 groupings of signals. And we don't see that. We just see a multiplet. So this is going to be ortho or meta, but we can't say for sure which one. Okay, so part B, again, I started with an HDI. Again, it was 4, so I'm thinking benzene ring. After all, this is the benzene ring chapter. For the carbon-13 NMR, we have 3 peaks, so we have 3 distinct types of carbons. And then for the proton NMR, we have what looks to be this does not appear to be writing. There we go. We have what looks to be 3 methyl groups. And then the second signal is going to be our aromatic protons. And so we only have 3 this time, so this is a tri-substituted ring. And the only way to make all this make sense is for an aromatic ring with 3 methyl groups on it. That's why this first signal is just a singlet. None of the methyl groups have neighboring protons. There's no protons on the adjacent carbons. And so they're just singlets. Okay, part C, I approached it the exact same way. So the HDI, again, is 4. Again, our IR doesn't really tell us much. It confirms the presence of a benzene ring. So we can go ahead and draw that in. And then looking at our NMR, I'm going to start at the bottom. So that's 7.3 ppm multiplet that integrates to 5. Tells us that this is a mono-substituted aromatic ring. And then our first two signals here are actually splitting each other. So we have a triplet, so we have a triplet that integrates to 3. So that's probably a methyl group. And then we have a quartet that integrates to 2. And so that's going to be a methylene group. And so they're splitting each other. The triplet is because it has 2 neighboring protons. The quartet is because it has 3 neighboring protons. And again, we know that this is just a mono-substituted ring. So we just have ethyl benzene. Okay, and so that's the answer to this problem. Again, it's just applying previous spectroscopic techniques that we learned to molecules containing a benzene ring. And that's the answer to chapter 17, problem number 55.